Alright, welcome back everyone. This is my 5th YouTube video, I think. I had to take a couple days off from recording every day and publishing. I'm really working hard on this video. I decided to do something brand new. I wasn't going to make a YouTube video on something I already did. And what we're going to be doing today, as you guys can see in the title and on the screen right now, we're going to be making a linear algebra library completely in Rust from scratch. Right, some of the things that this is going to do is row reduction, echelon form, inverses, determinants, cofactors, right? All of like the major linear algebra stuff that I remembered. I took it over a year ago now at this point. If you guys think of anything else that you want in this library for me to code on YouTube, let me know. Other than that though, I think we can just get started. Okay, so here we go. Let's zoom in. I always forget to do that before I start recording. Alright, we're not going to be doing much in the main function other than testing. What we're going to be doing in librs is actually constructing the library. So we're going to make our matrix struct. So pub struct matrix. This is going to have type usize. This is going to have type usize as well. I always forget the commas. And pub data, which is going to have type vec, vec f64. Okay. For the rest of the functions, I'm just going to be editing them to go at like a time lapse or something, speed them up, because some of them get pretty long. And I don't want to just be saying it out loud. I'll just explain what the functions do later. But anyway, we're going to put hashtag derive, and we want debug. This is going to be helpful when we have to ever print something out. I'm not going to be doing that on stream or on this video, but I was doing that when I did this originally 2 days ago. Okay, so first of all, here are our implementations on matrix. We just need the new function, obviously. Okay, so with the magic of editing, that went by fairly quickly, I hope. And all this does is it just constructs a vector of vectors, initializes everything to 0, and it just makes the matrix and returns the struct that we have here. We're not going to use this too often, but this was just the very first thing that I actually wrote up. The main matrix construction functions we're going to be using are going to be the next two. Pubfn from file. This is going to read a file, parse it, and construct the matrix based off of what is in the file. Okay, so this function, all it really does, it reads the contents of a file into a string. Don't worry about the unwrap or else, this is just some error checking. Then it has our matrix here. Oh, I forgot. We have to do matrix.push row. Alright, there we go. So all this is going to do, like I said, reads the contents of a file to a string. And then it splits the content up by new line characters, and then for each of those things in rows, so for rows in content.lines, we make a new vector, and we set entries equal to the strings that we split up with the white space, so like spaces, tabs, whatever, and then we collect them into a vector called entries, and for each string in entries, we push it onto the row vector after parsing it to a floating point number, 64-bit floating point number. And then our number of rows is the matrix length, and the number of columns here is just going to be the first element in the matrix's length. Now, what I could have done is I could have done some arrow checking to make sure all of the rows are of the same length, right, and all of the columns, I guess, but that's really tedious, and I don't really see the point. Ideally, you know, the matrix is going to be correct, and also I'm probably going to be the only one that uses this, and I'm going to know just to make the matrix right. I'm not going to make a mistake with the matrix. Now, alright, so what I'll do now is we can test some of this stuff. So in our main function here, we're going to use linalg, okay, and now we're going to do cargo run. Oh, and now we're going to do cargo run, and as we can see here, we have a 3x3 matrix, all zeros, and here we have a 2x2 matrix with 3, 5, 4, 9. If we do, I'll just cat it, cat source 2x2. We have 3, 5, 4, 9. Alright, perfect. So our first two functions look like they work. Here is the main function that I am going to use whenever I want to make a new matrix. It's going to be called pubfn from string. Alright, welcome back after that hopefully brief time lapse. So this is extremely similar to the read from file, because in the end the file is just collected into a string and then parsed. Here the only thing different, I'm not splitting it up by lines. What I'm actually doing is collecting the input after splitting it up by a semicolon. So what that's going to allow me to do is write a string like this. So if I say let m2 equal matrix from string, I can say it's 1, 2, 3, 4, 5, 6, and then 7, 8, 9, right? And so with this, I don't have to evenly space these out. Obviously, I could have like 50 spaces, but this is just to make it look nice for me. So let's do, oh wait. And then again, we can do a little println m2 cargo, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 3x3 matrix, pretty good, pretty cool. And now we're gonna be back here. Again, really simple function. This is just going to copy a matrix. Alright, so like I said, this just copies a matrix. I'm not even going to bother testing it. I kind of want to keep this video shorter than most of my other ones, if possible, because if not, this could be like a 15-minute video of me just coding. So it just has the new data initialized, and so then we're calling this like on a matrix dot copy, so we have a reference to self, so that way this function doesn't consume it, and then here we have for each row in self.data, so for each row in the matrix, we're going to push row.toVec. Now here you might be thinking, if you're like new to Rust, you might be saying, well, isn't row already a vector? What does that and sign mean? Well, essentially it's just a reference, right? And so I have to basically do toVector. I could have done row.toOwned, it's a similar function, but I just used toVec since it's just a more specialized version, I guess. But toOwned probably calls toVec once it figures out this is a vector. But anyway, if you're not familiar with Rust, I suggest just looking up ownership and scope rules and what it means when I have this ampersand in front of self.data and why I have to have it there. Otherwise, I get a warning like this. We're not going to be going into that in this video. I don't really feel like I'm qualified enough to give like a whole Rust explanation, but I know that I am qualified enough to make a linear algebra library.
Stop the cap. Stop the cap right now. Stop the cap. No bullshit, bro.
So here we just have a print function. Okay, so this extremely simple function just prints out the matrix. All this is really going to do, here we're using some actual Rust stuff, like what makes Rust different from more object-oriented languages. So here we're turning the vector, or I guess the matrix, but it is still technically a vector, into an iterator, and then for each item in that iterator, we use this anonymous function here, or a closure if you want to be that guy. We use this function here, and we have each item v, because since data is a vector of vectors, each iterator item is a vector of floating point numbers. And so then we're going to call println on this vector, and then we just make a new line at the end. So let's say I don't want to do this stuff anymore. I can just call instead m2.print. That's fine. I'm just not using those variables. But as you can see, this is what my m2.print function does. It's a little prettier than this. I could have done my own format display thing, but when you're working with a vector of vectors, it was getting just a little too complicated for me. And I said, I also just like this syntax here, m2.print. It's so much easier than println, exclamation point, quotes, right? I think it looks nice. So anyway, that's it for print. Okay, so here we're just iterating through the matrix, and we're setting each item along the diagonal, since we know it's a square matrix for an identity function, an identity matrix. We're setting each item along the diagonal equal to 1. I mean, nothing special about that. We honestly didn't even need that, but I just felt like, let's put it in there anyway. Now here is my favorite function that I made. I had a bunch of functions called scale, add, right, all of this stuff, but in the end, they're all doing the same thing. Or not add scalar, subtract scalar, right? We're going to go into adding two matrices and subtracting them. But here, when I was scaling or adding a scalar, whatever, they were all doing the same thing, plus, division, minus, right? I could just turn it into its own function by passing in my own closure, which would take an F64 and return an F64. And this is going to change the vector in place. So now we can do self.data. Okay, so I know this looks absolutely insane right now.
You're goddamn right.
Especially with the little Rust analyzer things going off on the right. But this is actually really simple, and I know I probably could have done it in a nicer way with just 2 for loops. But really, I love the way Rust has its functional programming stuff so easy. Compared to a language like C++, Lambda functions in Rust are incredibly simple, and they just look so much prettier. Especially in languages like Java too. Anyway, so here we take the matrix, turn it into an iterator. Now, as we saw in the previous function, print, we know when we turn the matrix into an iterator, each element is a vector, obviously. So then we're going to call map on each vector. And what the map function is going to do is turn each vector into another iterator. And each element there is a reference to an F64, since we still have this reference here. And now we're going to call F on X. Now X is this reference, we have to dereference it with the little star thing here. And then after that we call collect, so we collect everything up that we did with this map, and then we collect everything up again in the outer iteration thing from this map. So let's see what this looks like. So now if I have, we'll print M2 once, and then we're going to call m2.apply, and look at this, we're going to say this is our anonymous function, x times 2.0, since it's all floating point stuff. And then we're going to do m2.print. What's going on? Oh, alright, there we go. Look at that, boom, we multiply everything by 2 with such a simple function, right? I could have done m2.scale and just put in a 2, but this m2.apply thing could also just take an addition. I don't know, I really like that. I love working with the more functional programming ideas that Rust has. I'm a big functional programming guy. I know some people don't like it, but I love Scheme, love OCaml. I don't know enough Haskell yet. Erlang is okay. And what was another language? I was trying to learn another functional programming language. I don't remember though, because I've been really focusing on OCaml and Rust right now. Anyway. Alright, here we go. Very simple. It's just adding two matrices together. I probably could have done it with some iterators and some mappings. I would have had to zip up the two vectors, but there comes a point where even I don't want something to look as unreadable as this. And this works just as well, and it's just as fast. So then we're going to have our subtract function, and it's literally just going to be the same exact thing. Alright, I mean, here's subtract. Really nothing special about that. Here is the first actual interesting function. We're going to take the dot product of the two matrices. Hey, welcome back again. So essentially here, as we know for the dot product, the first, if you have like matrix A dot B, A has to have the same number of rows as B has columns, and A has the same number of columns as B has rows. And so here we iterate through A's rows and B's columns, because remember, let's say there are two. We're taking the first step, right? So we multiply everything in the first row by its corresponding element in the second matrice's first column, right? And then to do that, we have to iterate through the second one's rows as well to just grab the first item or the corresponding item in the rows. So for each row, we take that row, and then for each column, we will do the multiplication that we need to do and sum everything up and then put it in its corresponding place in the dot product matrix. Here we're going to have our row reduce echelon form function. So this function just swaps two rows. We have to do this clone thing again because of the whole reference issue here. It's not even an issue, the whole reference idea here. We just have to clone it so that we make a brand new vector. Otherwise, if we set this equal to just nothing without the clone here, it would just be set equal to that same place in memory, I believe. Whereas here, if we do the clone, we construct a whole new vector, and then we're able to just put it into place using these next two lines of swapping. So back up here to the reduced echelon form. Okay, so what this is going to do for us is essentially, I'm going to pull up what I used to actually do all of this. So here's the algorithm for row reduction. And essentially all it does, we need to check if the leftmost entry in the first row is equal to 0. If it is, we have to get something that's not equal to 0. So we just have to swap the rows, which is what swap rows does here. We do that check and then we're done. Then here we scale the first row so that its first non-zero entry is equal to 1. That is just what this div thing is doing here. So we get the first entry set it equal to 1 by dividing it by div, right? What does this if statement do? And lead, what is lead? Right, very confusing stuff. Lead is essentially the row that we're on right now. So we start at row 0 and then we increment it. So originally lead is equal to 0. We're on the 0th row. And so we take the first element and that's what we want to work with. So then if r is equal to lead, we just divide everything by what we need to make that first entry equal to 1. That's exactly what it says here. Scale the first row so that its first non-zero entry is equal to 1. And then use row replacement so all entries below this 1 are 0. That's what this does here. So if r is not equal to lead, for each column in this row, we take it and we subtract it by the item above it. So lead is the column, lead is the row that we are currently working on. I think in linear algebra it was called the pivot. Lead has the pivot, right? And then for each row below it, we subtract the corresponding item from the top, and then by the multiple that we need it by. And then you just keep doing that over and over. So again, use a replacement so all entries below this 1 are 0. And essentially you end up with something like this, and it doesn't matter what's in here. And what does correct do? Well, correct is going to be another function down here. Sometimes when we do these matrix multiplication things with floating point numbers, it's not even a matrix thing, it's really just when we do it with floating point numbers, we could get the issue where they are extremely close to 0 or extremely close to another number. For example, I was getting something where I had one of my matrix elements had the entry 1.999999999. I mean, that's just 2, right? I'm not gonna leave that. So that's what this is doing. We're gonna correct some of that stuff. And also, you could get, when you print it out, you could get like a -0. All that's saying is it's not really 0, but it's close enough to 0. It's just a floating point thing. I don't even understand it really, to be honest with you. But we're just gonna fix that here. and then we can floor the number. Okay, so here, like I said, we could get some like -0 issues. It must just be a floating point arithmetic thing, so we just set it equal to 0. And now here we could get something like 1.9999, so we floor it, get it down to 1. If it's like greater than this, we just round it up to 2, for example, or whatever the original number would be rounded up to. And now here, these two things essentially do the same thing. If it's greater than 0 but less than this extremely small number, we're just going to say it's 0. If it's less than 0 but it's greater than this extremely small negative number, we just set it equal to 0. And so that's it for correct. Now, I don't know about you guys, but I always hated row reduced echelon form. It all seemed very hand-wavy to me. However, actually coding it up and reading the explanation and stuff, I felt like I was learning it again at a deeper level, more in-depth almost. But anyway, now we're going to do something fun, something that I really liked in linear algebra, and that's the determinant. So we're going to return a new matrix. Actually, no, for the determinant, we just return an F64. And I'll see you guys in a second. Okay, so essentially all this is the determinant. Now, there are two ways that I know of to find the determinant. You could do it the way we do it for 2x2 matrices, right? If the matrix is AB and then CD, you do A times D minus B times C. But when you have bigger matrices, like 3x3, 4x4, that gets so much more complicated in my opinion. You got to start wrapping around to the beginning of the next line once you reach the end of the top line. Then you have to go backwards to subtract. It's so confusing. And I remembered there's another way to do it. You use cofactors. And with the cofactor, I'll show you guys what I used. We use cofactor expansion. So now, when you expand upon a row, I always expand upon row 1, which is really the second row since we're 0 indexed. But these people here, they have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, right? The determinant of A is equal to -1 times the row you're on plus the column you're on. I is going to be their row. And then here you do A of ij, which is the element at oh, here we go. Here's a perfect example. So here, let's say you expand upon row 2, which is exactly what I'm doing, except here my row would be called row 1, but it's the same thing. So you do -1 to the power of the row plus the column you're on, multiplied by the elements at that spot. So you do A at row 2, column 1. Row 2, column 1 is 4. Then you multiply that by the determinant of A 2 bar 1. I don't know how you would say that, but essentially all that does is you remove row 2, column 1. So then you get the matrix 2, 3, 8, 9. So this is like the craziest part. The determinant has a recursive definition that you can use. And that's perfect for programming, right? And then it's the same thing over and over. You're in column 2, then column 3. And this goes on and on for if you have a 4x4, 5x5 matrix, it's the same thing. So now let's code up the cofactor function. Okay, so here is the cofactor function, and it's exactly like I said. This section over here is making the smaller matrix by eliminating the expanded row and the column that we want. So here, I'm iterating through each column on the row I want to expand upon. So like I said, I'm expanding upon row 1, technically row 0, right? Remember? I mean, not row 0, row 2, because row 0 indexed. So we expand upon the second row, and then we expand upon the second row, and then for each column, we send the column into the cofactor function with the row, and we multiply it by the element at the matrix spot there. We multiply it by A21 here, and it'd be the same as A21 here. And so then in cofactor, we make the new matrix by iterating through the whole thing and ignoring the row and column we don't want. So here we have if R equals expanded row, we just continue, and if C equals the column that we don't want, we just continue. So here again, like I said, it's row 2, column 1. We would iterate through here, row 2, column 1. Oh, this is column 1, so we ignore it. We push 2 and 3 into the first vector, and then we push the first vector into cut. Cut is the new matrix that we're making. I just wanted to name it cut because I felt like I was cutting up the old matrix. And so then we're on the next row, row 2. But wait a second, we want to eliminate row 2. So our first if check over here registers, and then we continue. So we ignore the entire row 2. And then here we're on row 3. Oh, we're on column 1 right now. We ignore the 7, we push 8, 9, we get this 2, 3, 8, 9 as the new matrix, and essentially all we do is call determinant on that matrix. And since in this example right now, since our original one is a 3 by 3, cut here is going to be, or minor here is going to be a 2 by 2 matrix, and then we just return this. So like I said, determinant, finding the determinant of a matrix is a recursive function with the cofactors. The cofactors require the determinant, and the determinant requires the cofactors. I don't know, to me, it just blows my mind that it works out like that, and how easy it is to code it up. And then again here, this is the minor is the determinant. So we have our minor here, and we multiply it by the element. So, we multiply it by the element over here, sorry. And then we multiply it by -1 to the power of the row that we're on plus the column. I have to cast this to an unsigned 32-bit integer. I don't really know why it couldn't be U64, because the U size is U64 on my laptop. But whatever, that's what you have to do. And then I cast it to an F64. But yeah, and then like I said, this is going to return this. So this is here, and then we multiply it by the element at that row and column that we're on. I found this amazing. When this worked and I was able to run it, I found it so cool. And we're going to do that right now. So let's do here we go. M4 equal matrix. Like I said, the from string function is the one that I pretty much always use. So we're going to clear the screen, cargo run that. The determinant is 132. I know this is correct. I tested it before. I forgot to pull up a determinant calculator on Firefox. If you guys want to test that out later, you can. And I'm not going to do that right now because my laptop is burning up for some reason. Whenever I record with OBS Studio, I don't know, just starts going crazy. So honestly, in my opinion, that was the highlight of the video. The determinant was my favorite part of this whole program. But we still have two more functions left, the transpose and the inverse. Alright, here's the transpose. It's really simple. You just swap the elements. So we make the transpose matrix. It has, for rows, the number of columns that the original one has, and for columns it has the number of rows the original one has. And so then we just take the element at the transpose ji equals the element at the original one at ij. You're just flipping it over the diagonal, nothing really special about this. Alright, now we got the inverse. Okay, we're back. Now, inverse is another cool function. I like it because we're using four functions that we already made, and 3 of the 4 are my favorite ones. So let's take a look. Here we calculate the determinant of the original matrix. Like I said, if the determinant, or not like I said, like everybody knows, if the determinant of this matrix is 0, then there's no inverse. That's just a linear algebra property, and we know that has to be true, because then if the determinant is 0, we can't divide everything by the determinant, right? Because you can't divide by 0. So then, here is the really fun part, right? We calculated the determinant, but then you can use the inverse. You can find the inverse of a matrix using the cofactors that we just coded, right? So here, you make the matrix of minors, and then you turn it into a matrix of cofactors, right? I already made the minors in the cofactor function. Where is that? Here. See, I made the minors. All I need to do is make the matrix of cofactors, and I can just use the function for that. So for the matrix of cofactors, each item in the matrix, so at row 1, column 1, right, the top leftmost element, the item there is the cofactor if you expand it upon that row and that element, right? So you would just call the cofactor function on that row and column, and then you set whatever you get equal to what you put that in the spot of the inverse. So at that row and column in the inverse is the cofactor of the original matrix in that row and column. I feel like I completely messed that up, but I don't know. I'm getting tired of talking so much. It's really making me mess up. So then here, we correct the matrix again, because you can get that weird -0 thing and really small or really close numbers. And then you call the transpose on the inverse, and then you multiply the inverse by the inverse of the determinant. So the adjacent, they call it, or the adjoint, you transpose the matrix, and you multiply by 1 over the determinant. And boom, this might be the highlight of the video, this. But yeah, anyway, I'm going to paste some tests from when I did this originally into the main function and show you guys what it looks like. And yeah, I'll be right back. Okay, I'm back. This is what I originally was working with when I wrote this up yesterday and the day before. This tests pretty much everything, right? We're testing the determinant, copy, apply, identity, print, the inverse, and row reduce echelon form. So here, let's go back to Alright, so here, this is what we get from testing everything. Everything looks good to me, right, when we test apply. It was the second time, 99, and it was M4 transpose. Yeah, that looks good. The inverse here of M5 is 302, 2, 0, negative 2. I had that one here. The original matrix on this web page was 302, 2, negative 2, 0, 1, 1, which is exactly like I have here. My computer is lagging so much right now. And then they say that the inverse here is 0.2, 0.2, 0, negative 0.2. Let's see if I can do this. 0.2, 0.2, 0, negative 0.2, 3, 1. Yep. So our inverse works and our row reduced echelon form works because I have that answer right here calculated. 1, 0, 0, 2, 0, 1, 0, 4, 0, 0, 1, negative 3. Alright. And yes, the determinant of this is 0. The determinant of 27 minus 20 is 7. And the determinant of M4 is 132. I remember that. Everything looks good. I could have written like an actual Rust test. I did not feel like it. But anyway, I hope you guys enjoyed this video. I worked really hard on this one, and I'm going to work even harder when I edit it tonight for like the next 4 hours. But yeah, if you enjoyed it, please absolutely smash that like button. Don't forget to subscribe, leave a comment. Yeah, let me know what you guys want to see next. If you want anything else for linear algebra in here. That's it. Peace out.